Back at it with more sample problems. This is 1427 from the end of chapter questions in your textbook. It asks, given a reaction, carbon monoxide combines with 2 copies of hydrogen to make methanol. It's a gas phase reaction, so they chose to give us a Kp rather than a Kc here. And the value of that is 22,600 at room temperature, 298 Kelvin or 25 degrees Celsius. They give us this information and they want us to compute the equilibrium constant that we would expect for a series of reactions based upon the given information. This problem involves the rules that we discussed in class that allow us to predict the equilibrium constant for a different reaction. And basically there's 3. One deals with the reversal of reactions. We're going to use that here. Another rule deals with multiplication of reactions by a value, oftentimes an integer, but in some cases it can be a fraction. We're going to see that rule here. And the third rule we talked about was for summing reactions. We're actually not going to use that one here because we can get away with just using the first 2. But if you ever would have to sum reactions or add 2 reactions together, the resulting reaction is the product of the equilibrium constants of what you have to add together. Okay, so let's see how this particular problem can be worked. We'll start with A and we'll work our way through. So the trick is comparing the reaction that you're trying to find the equilibrium constant for with the original. And there's usually some kind of relationship between the two, okay? Now, as I look at this reaction, I see that here methanol is listed on the left of the arrow. It's the reactant and it decomposes to 2 copies of hydrogen and carbon monoxide. That is exactly the opposite of this. We basically just flip the reactants and the products, okay? So this one's pretty easy because this is just the reverse reaction. And the rule tells us that the equilibrium constant for the reverse reaction, I'm going to abbreviate that K sub ReV here for lack of any better term for reverse. And that is equal to 1 over the K for the original reaction. So if you reverse a reaction, you take the inverse, okay? So to solve for this K, I have to take 1 over the Kp value, which here is 22,600. If I do the math on that, I get 4.42 times 10 to the minus 5th is my value, okay? So for this reaction, I didn't know anything about that going into it, but now I can express that I expect the Kp for part A to be 4.42 times 10 to the minus 5. Just by using this rule. Now, remember what these values tell you about, okay? Remember what the values tell you about. The magnitude or the size of the value tells you whether or not you're product favored or reactant favored. If Kp is a very big number, say greater than 1,000, you've got mostly products existing once equilibrium is reached. If Kp is a very small number, say less than 0.001, you've got mostly reactants. If K is an intermediate value, you have a little bit of both present in your reaction system once the system reaches equilibrium. You've got all these substances present at the same time, okay? So that's what Kp tells me. So the fact that Kp is very small for reaction A tells me that this reaction doesn't really take off appreciably. And at equilibrium, I've got mostly methanol and very little undergoes this reaction. However, this reaction, the first given reaction, because its K is so big, that tells me that if I mix these guys under the right conditions here, this equilibrium takes off to the right and we get methanol production. So that's what the significance of the value of K is, the size of K. All right, so we worked problem A. Let's move on and work some more. Problem B. It asks us to calculate K for a different reaction. In this reaction, we're taking a half a copy or unit of carbon monoxide, combining with 1 hydrogen to make half of methanol. Now if I compare this reaction with this reaction, they actually look really similar. The substances involved as the reactants are the same. The substance that's produced as a product is also the same. The only difference is the numbers out in front, these so-called stoichiometric coefficients. Here they're 1/2, whereas here it was 1, and this was a 2, and now it's only 1. So it looks like to generate this new reaction, I have to multiply the first reaction by a half. Okay. Now, why is that significant, this multiplication by a half? Well, my rule that we learned about in class tells me that the new equilibrium constant that can be generated when you're multiplying a reaction by a number equals the original K value, this is the one we're given, okay, raised to that number n, where n is the number you multiply. So basically what this equation tells me to do, that if I want to figure out the answer to part B, get my new Kp value, I have to take my original number, which was 22,600, and multiply that to the 1/2 power, which is basically the same as taking the square root. Okay, mathematically that's no different. So if we do that, we end up getting 150.3 from my new value of K. That's the answer to part B. So all I had to do was multiply my values by half, and the rule tells me to compute the new equilibrium constant. I take the original K and raise that K to the power of whatever I multiply by. If I multiplied by 2, this would be a 2. If I multiplied by 5, this would be a 5. Here I had to multiply by half to make it work, so I have to take the square root and get the 150.3. Okay, so Kp for the second reaction, right about 150. All right, let's move on. What about part C? Part C, we've got a reaction in which 2 copies of methanol decompose to carbon monoxide and 4 copies of hydrogen. Now, if I compare the reaction in part C with what I observe in part A, I see 2 things are different. Okay, one is we flip-flopped or reversed the reactants and the products. Here, this is a product. Now it's a reactant. These guys are our products here, but they're a reactant over here. So we've reversed the reaction. Okay, so if I'm making a sort of a list of what needs to be done to the original, one thing is I need to reverse it. But that's not all. That's not all. Because it looks like I've also done what? Multiplied this reaction by integer 2. Here I've got 1 copy of everything. Here I've got 2 and 4. Okay, so 1, 2, 1, and 2, 2, 4. So I multiply the reaction by 2 down here. Okay, so those are 2 steps. But it doesn't really need to scare us, because what we can do is we can solve for the new K value using our rules. And we just do a sequential approach, okay? So the first thing I'll do is reverse the reaction. Reverse the reaction. And remember, if you do that, just like we learned in part A, you take the inverse. We actually already did that calculation. I'll call that K REV 4.42 times 10 to the minus 5. All right, so that's going to be my reversed K. Now, I also need to multiply this reaction by an integer, by 2. So what I really need to do to get my overall new K for this reaction is I take this reverse value, 4.42 times 10 to the minus 5th, and I apply that second rule that we learned about, where I raise it to the power that I multiply by. So I reversed in the first step to account for the difference in the reactants and the products. They're identities, right? Because I flip-flop what's being reacted and what's being produced. So I have to account for that. So I do my reversal step first. And then I take the value that I got after I reversed the K, and I raise that to the second power. This 2 is because of the 2, and the fact that I multiply this 2 by 2. So I multiply the reaction by 2, the original reaction by 2, and I get this, okay? So sure enough, that's the only step that I need to get complete. And if I do that, I get 1.96 times 10 to the minus 9. That's my Kp value. All right, so this is how we basically solve this problem. Now, the question again goes on to ask about which are favored products or reactants, okay? And basically just to give you an idea of what that means, they're basically asking us, will we have more products or more reactants once the system reaches equilibrium? And the value of the K tells us that, okay? If K, we'll say, is larger than 1,000, all right? If that's the case, the products are favored. Okay? K is a very big number, we'll say bigger than 1,000. The products are favored. And what that means is we have a case like in the first reaction here, where K is very, very big. What that means is that if you mix these two in a flask in the gas phase, that they tend to form the methanol very, very vigorously to a large extent, okay? At equilibrium, we've got a lot of the methanol and not very much of these, okay? And of course, the reason why that is because the equilibrium constant is defined as the partial pressures of the products divided by the reactants raised to their stoichiometric coefficient. So we can see if K is a big number, the products are favored, and we have a large concentration of this at equilibrium, but not so much of these at equilibrium. There might be some present, but not a lot. Now, another option is what if K takes on intermediate values? Another option is if K takes on intermediate values. Here, I mean that's between about 0.001 and 1,000. Then it turns out that both reactants and products are present at equilibrium. We'd have a mixture. Okay, so do we have a case like that? This is a good example of that. Okay, so in this case, the K is about 150. So what that means is that the ratio between these and these raised to their stoichiometric coefficients will be 150. Okay. But the thing is that sort of suggests that we've got a mixture of both of those present. All these substances would be present at equilibrium once equilibrium is reached. Now, because this is a good bit above, say, around 1 or so, we have mostly this still, okay? But there'd be a bit of a mixture between things, okay? So the K value tells us kind of where this equilibrium stands. Now, the last possibility. On the PDI, I gotta see it. Do you see it? Last possibility is if K is very small. Let's say that K is less than 0.001. If K is a tiny, tiny number, say less than 0.001, that means that the reactants are favored, that we mostly have reactants at equilibrium, and the reaction does not proceed very far to the right. We have mostly reactants, and K is very, very small, okay? So this is the magnitude of K and what it means. And this is an example to show how we can manipulate K values and generate K values for different reactions that we originally knew nothing about. So this is one example problem for this chapter.